Hey guys, it's your boy, Snert here. Snurting makes me feel good. And today we got a little bit of a different video. We're still on HackerRank, but in the previous video that I uploaded, which will be sometime in the past now, I got a comment and the analog dude, he's like, try this one. And he gave me a link to a maximum subarray sum. And I'm just going to say right now, I'm putting my foot down. I am not going to accept any suggestions for problems because the thing is, for this HackerRank thing, I'm doing the interview preparation kit because it's good. The problems aren't too difficult, so it's easy for me to make the videos. And the problems aren't too hard, so it doesn't turn a bunch of people off. And it's good practice. It's a practical skill because many companies use problems at that level. Those problems were selected because they're kind of a similar difficulty level to things that you might encounter in an interview. Whereas problems like this are probably more difficult than you would encounter in your average coding interview. So I'm not going to be accepting, challenges from people, Chili, solve this one, or, requests for help because they can't solve them themselves. That's not going to happen. That'll just waste too much of my time. That being said, I couldn't help but click the link. And once I read the problem, I'm like, I'm not going to do this. It's a hard problem. I believe the success rate for this one is around like 30%, which is quite low for this website. Most hard problems are closer to like 40 or 50%. So it's a fairly difficult problem. But once I read the problem, I just couldn't stop thinking about it. And I ended up solving it basically in my head while doing other things. And I figured, well, if I already solved it, I might as well, try and code it up and see if I could do it. And I did, write the program and it worked. So I figured, well, I've done all the work. I might as well make the freaking video for it. So here's your freaking video. It's the first one. It's the last one. Just to give myself a little more, to boost my my ego up a little bit more. He said, a few days ago, I have spoke to a guy who makes his living, quote unquote, programming C++ in California. And even he couldn't solve the problem. So the quote unquote programmer from California couldn't solve this problem. And that means it's some hard shit. You're in for a ride. All right. So enough preamble. Let's get to the freaking problem, all right? So, a subarray of array A length n is a contiguous segment from basically element I to element j inclusive. So here they define a subarray as a contiguous subset of, the super array A. And the sum of an array is the sum of its elements. Okay, this isn't too hard. This isn't too bad. Given an n-element array of integers and an integer m, determine the maximum value of the sum of any of its subarrays modulo m. Now, let me just say one thing. If you are an alpha male or an alpha female, as the case may be, then you must pause this video right now, close the video, go to HackerRank, go to this problem, solve the problem. Don't watch the video until you've solved the problem. If you watch the video and you haven't solved the problem, at least if you haven't attempted the problem, then you're a coward. I'm sorry, but that's the truth. That being said, now we're going to go over the solution. It's going to be a bit of a ride. So, this is a very common thing that you're going to see in competitive programming and programming problems. Modular arithmetic. A lot of times the questions will have numbers that will definitely overflow out of the maximum size that you can get in your standard machine-sized integer, right? 32 or 64-bit integer. And so what they do is they say, okay, well, give us the answer modulo some value. And what that means is that it's the modulus, right? I hope you guys understand what a modulus is. It's basically integer division. Honestly, if I have to explain this, then this isn't the problem for you. But just to make it clear, if you had a number like, let's say 12 modulus 7, the result of this would be 5, right? That's a 5. Why? Well, because if you divide 12 by 7, it will go into 12 one time, so that's 7. And the remainder after that division would be 12 minus 7, which is 5. That's what modulus is. It's the other side of the coin of integer division. Integer division gives you the quotient, how many times a number goes into another number, and modulus gives you the remainder, what's left over after you've gone into it that many times. So what we're going to do is we're going to have, an array, and you could have any number of subarrays, like from here to here could be a subarray, or from here to here could be a subarray, or from here to here could be a subarray. You've got a lot of different possible subarrays, and you take the sum of all the elements in that subarray and you modulus it by some modulo m, and that gives you the result. And we want the subarray that will maximize that modulus of the sum. Now, before we actually get into the real solution to the problem, let's do something that I often do in coding challenges, especially ones where you don't have a lot of feedback on whether your answers are correct or whether there's a penalty for submitting answers if you get it wrong. And what I do is I like to first code up a brute force answer, a very simple answer that will time out on a real data set, but that can be used on smaller data sets to validate your assumptions or validate your more optimized algorithms. So let's just start with a very simple brute force approach. What would that be? Well, we just examine all possible subarrays. So what we do is we would start here and we'd say, okay, well, here's one subarray. That's this element here. These circles here, they're not zeros, they're just elements. Give me a better color here. Yeah, that's better. So then we do this one. We take the sum of this value and we modulo by m. Then we add this value and modulo by m, and we add this one, and we keep updating a maximum. We've got some variable here, which is our best answer. And after adding a element, we get the new modulo sum and we update the maximum. So we keep doing that till we get to the end. Then we go again. We start here. So now we start from here and we add another one, another one, and another one, and another one. And we keep doing that until we've reached the end. And we will have examined all subarrays, because we have all of these ones here and all of the intermediate sums, because every time we add a new element, that is one more subarray that we are evaluating. So it's not just this is one subarray. No, this is one subarray, this is one subarray, this is one subarray, you get a subarray, you get a subarray, subarrays for everyone. I'm the Oprah of subarrays. So we're going to write this brute force approach, and maybe that will give us some insights, maybe it won't. But I figure, why the heck not? By the way, this is probably going to be like a pretty long video. I'm sure you can look at the bottom of the video and you can see the length of the bar there that allows you to scroll. So I just like to modify my input here. And the way that this works with the modular arithmetic and everything, all the inputs are positive. I don't really see a need to treat these longs as signed. I don't know, it probably doesn't make a difference. But I like to do problems like this with unsigned arithmetic. So I'm actually going to do something a little crazy here. And I'm going to reinterpret this vector of longs as a vector of unsigned longs. Honestly, this is probably like a don't try this at home kids moment, but I don't know. It makes me feel better for some reason. And it doesn't actually hurt the result, as you'll see at the end. So, and we'll also make our mod unsigned long cast from m. Okay, so these are inputs cast to unsigned types. And okay, so what we're going to do is we're going to have an unsigned long maximum equal to 0. And now we're going to start our first loop, which sets the start of each section of subarrays, each subarray sequence. So for auto I is equal to input.begin as long as I is less than input.end I plus plus. Yes. Okay. So that's basically the loop. Where's my freaking, yeah, that's the loop that will give us this start, this start, this start, this start, this start. Now we got a loop that is going to loop across each of the elements from that start to the end of the main array. And that is going to be, let's do unsigned long sum. So across this one input here, we're going to be maintaining a partial sum that builds up. And every time we add a new element, that's going to be the sum for another subarray. And then we're going to update that into the maximum. So we need to keep track of the sum. And for auto j is equal to I. I don't like it. There's a bit of dissonance, cognitive dissonance here in my head. I can't talk while I'm typing, doesn't work too well. Begin. No. As long as I is less than input.end. Wait, j plus plus. So part of me is like, don't use I and j for your looping elements because they look too similar. And another part of me is, but chili, that's what you've been doing for your whole life. So, you know, there's that. Sum is equal to, okay, so here's the thing about modular arithmetic. The main thing that you need to know about it, and it's right here. If you want to find a plus b mod m, that is equivalent to taking the modulus of a and the modulus of b and then adding them together and then taking the modulus of m of the result. Now, why is this important, you might say? Well, if a and b added together have the ability to overflow, that's going to be a big problem. If you overflow, your result is no longer going to be valid. So if you can modulus before you add, modulus will, you know, bring the value down to within a specific range. Like if you mod 100, your value can never be greater. The result can never be greater than 100. So by doing the modulus and then adding, what you'll have is you can prevent cases where adding first might cause an overflow. So to understand when you would need to do this, you really have to go back to the problem. You have to go back to the constraints and see, okay, how large are my values? So they can be up to 10 to the 18. The modulus, 10 to the 14, there's a big difference between that. And the number of elements in the array is 10 to the 5. So basically, if you take this maximum and you multiply it by 10 to the 5, that will get you your maximum sum. So your maximum sum would be 10 to the 23, which is going to overflow a 64-bit integer. You can see here that we're very close to the top end of a 64-bit integer. Actually, I'm not exactly sure now that you mention it. So 2 to the 64, it's really 2 to the 64 minus 1. Yeah, so that is 1.8 exponent 19, so times 10 to the 19. So we've got like one digit of leeway here. And I've added a little extra leeway because I've cast the numbers to unsigned. So when I do all my operations in unsigned, I get an extra bit, binary bit. But you can see here that these will overflow quickly if you don't mod them first. But if you mod them, you could add them all together and you wouldn't overflow. And that might be useful information for later on. But for right now, we just got to realize that we're going to have to be doing some modifications here. Mod this bitch up. What we're going to do is we're going to say, okay, so the sum is equal to the previous sum value plus the current newly added element mod our mod value, and then we're also going to mod that by the mod. Now we actually don't need to do this. I believe you don't need to mod twice, but we'll cross that bridge when we come to it. Then the maximum, this is the maximum sum, modded sum of all subarrays that we've seen so far is equal to the maximum between the current maximum and the sum that we have of the current built up subarray. And then we're just going to return, long maximum. Yeah. All right. So I believe that this should give us, this should be correct. It's going to be too slow. I already know this, but yeah, I think it'll run if I haven't messed anything up. And I think it'll pass all of the simple tests. Yeah, and there you go. Pass sample test 0, 1, and 2. All right. Now, let's submit the code and see how bad it fails. It should fail pretty badly. All right, so we've passed some test cases here. And so we passed the sample test cases. Terminated. Yeah, I got that. Let me scroll, bro. Yeah, so we passed a bunch of test cases. 1, 2, 3, well, 3 non-sample and 3 sample. So we've passed 6 altogether. But we have failed, you know, however many are left. I don't know. I'm not going to do the math. It doesn't freaking matter. I think it's 12. We still fail in 12 cases. If we look at them all, the only failures that we get are your code did not execute within time limits. So this tells us that probably, I mean, it's not 100% guaranteed, but probably this algorithm is correct. It's just too slow. It's just too freaking slow. Now, here's the thing. Our sum here, this is mod whatever. And the maximum that this value can be is 10 to the 14. So sum will never be greater than 10 to the 14. And j will never be greater than 10 to the 18. So if you add 10 to the 14 to 10 to the 18, it's not going to overflow a 64-bit integer, which means that we don't have to do this preemptive mod here. All we need to do is do the sum. We add j into the sum, and then we want to mod the result to clamp that to within 10 to the 14. So we can get rid of one modulus. Now, modulus is done by integer division, which is quite a slow operation. This isn't going to change our time complexity. Our time complexity here is, you can see it's a nested loop. Our time complexity is right now n squared. This is not going to change our time complexity, but it will change, you know, the k that is applied to that. And that might be enough to pass some more test cases. So let's just try and submit the code with that one minor change. And if my intuition is correct, we will not fail any additional test cases. But we might pass some other ones. And I believe we did pass a couple of new test cases. So yeah, before we passed 6, now we've got 1, 2, 3, 4, 5, 6, 7, 8. So we passed 2 additional test cases by removing that mod. Again, it's not going to move the needle enough for us to care about. But it's just interesting, just to show you guys that we didn't need both those mods if we examine the parameters of the problem. So on the rest of the test cases are all still just timing out. So probably our algorithm here is still correct. It's just n squared is too slow. N squared is probably going to be too slow, and we could do another test. We could say, okay, well, what if we remove this other mod? Now, if we remove that mod, the answer will be wrong. We will fail most of our test cases. But what if we don't ever time out? If that's true, then we might even be able to solve this problem with an n squared time complexity. So let's look at here. Okay, wrong, 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 wrong. They're all wrong. Nope, we still get some that time out. So even removing all of the expensive operations, we see that no, you're not going to get anywhere until you improve your big O. The big O is where it's at. Your little mini, your micro optimizations, they'll get you a little bit something here and there, but in the big scheme of things, they aren't worth poopy. They're not even worth a snort in the wind. So now comes the meat of the problem. 25 minutes into this recording session, I don't know how many minutes that is once I, edit it down, but now we actually have to earn our keep. We've got to figure out a smarter way of processing this data to be able to get it done within the time constraints. And this is basically where all that work happened that I told you about, where I thought of this stuff in my head as I was basically doing other stuff, as I was walking around, doing shopping and stuff. That's where this problem got solved. And that's where I started to think of, well, let me tell you what I thought of. So basically what we're doing here is for every one of these iterations, each one of these lines here, that's an iteration of I. And every one of these is an iteration of j. And for every one of these, we are building up a sum. So if this was like 0, this one might be 4, and then 8, and then 16. And let's say this was mod 20, so the next one would be 0. And I don't know, it depends on what numbers are in here, right? But this is assuming they're all the same number. Anyways, it doesn't freaking matter. Not the same number, because this is 8, and it doesn't matter. It doesn't freaking matter. What matters is that we're building up a partial sum here, and then we're going to build up another partial sum here. Now, what we could do, what I thought of, just the thing that my brain went to, is what if we first do the entire partial sum ahead of time? Meaning, we turn this array of values. Well, let's not pussyfoot around. Let's use some actual numbers here. It'll be a lot easier to explain with real numbers to deal with. So we'll use the example from, the problem here. 33995 mod 7. So that's our array here. Now let's tabulate the partial sum. So what is that? Well, 3, 6, right? Now we add 9 to 6, that's 15, but it's mod 7, so that's 1, right? 15 divided by 7 is 2, remainder 1. Then we add 9 to that, that's 10. 10 mod 7 is 3. And then we do what? Then we add 5. 5 plus 3 is 8. That is 1. Right, okay. So this is our partial sum in mod 7 space. Now what does this give us? Well, I'm going to tell you, it doesn't give us much at this point. But it's just an idea that I had. And then I thought to myself, well, let's back it up for a second. What if we just took a normal partial sum, not mod 7? What would it be? Again, it would be 3, 6, 15, 24, 29. All right. So if I wanted to find the sum of any subarray, now that starts at the beginning and goes to any given element, I just got to look at this value. So if I wanted to get, this subarray, I just have to look up this value. I don't have to add them all together because I have this. And the question in my mind was, does this help me? As opposed to my other algorithm there. Not really. But I thought, what could I do? Like, this gives me any subarray starting from the beginning. But what about a subarray starting from here? Or what about like this subarray here? I can't just say, okay, well, it's this number, because it's not. This number here is this subarray. But I want the value for this subarray. What is that? Well, this subarray is actually just the whole subarray minus this part. So if I take 29 and I subtract 6, 23, that's the sum of these three values. 9 and 9 is 18, and 5 is 23. Now, here is something. Because this will allow us, if we wanted to do a query and say, okay, what is the sum of this subarray? Instead of having to sum all those values up, all we got to do is look up into this partial sum, two values, and subtract them. So that takes a big O of n operation, and it reduces it down to big O of 1. Now, the problem is, there's a bunch of problems. First of all, we're not dealing with a normal sum. We're dealing with a sum mod 7. And the second problem is, the bigger problem, is that even if we reduce this query down to big O of 1, we still have to examine all sub-ranges. And there are n squared sub-ranges. So we're still at a big O of n squared time. It's just we're doing a different operation. Because in the brute force method that I've already shown, the query for the subarray is based on the previous query, and so we just build it up by one element every time. So in this one, the query is big O of n, it's constant time, because we're building up from the previous query. Whereas in this solution here, we can do just a random query from any point to any point without having to build the whole thing up. We can just query here and here, and then we can query a different part in any order we like. So it's more freedom, but it's still the same big O of n. The problem is that we have to examine all n squared subarrays. And so we're never going to get better than n squared time complexity. So we've got to somehow find a way of avoiding examining every single possible subarray. And if we do that, part of that might entail querying out of order, in which case this technique will come in handy. These are the ideas that go through my mind as I'm pondering a problem, although I'm putting them in words now, but they don't come out in words in your brain as you're visualizing it. It's just, you visualize like arrays of numbers and basically something similar to what I'm drawing on the screen here, and different manipulations and how would they affect each other. It's weird. I don't know. When they invent a camera that can go inside your brain, then maybe I can show you. But for right now, this is an interesting idea. This partial sum that we can use to do a 2-point query and find the sum of any subarray, not just a subarray starting at the beginning. Useful tech. Now let's go back to the modded partial sum. Can we do the same thing for the modded partial sum? Could I get the modded partial sum of this subarray using my modded partial sum here, the entire modded partial sum from the beginning to the end? Can I use this to get a partial sum of a subarray? Well, first let's find the modded sum of this. 9 plus 9 is 18, 27. 27 mod 7 is 27 minus 21, which is 2. Okay, so this is the answer, 2. Well, the technique would be the same, right? We would subtract this partial sum here from this entire partial sum here, which means basically 1 minus 6. But this is all mod 7. Now, if you want to visualize what this modular arithmetic BS kind of looks like, you should visualize it as a circle, as a ring. There's fields of mathematics called discrete mathematics that deal with things like, well, fields and rings and just algebras and stuffs like that I've studied in university and that I vaguely remember. But if there's one thing that doing a lot of that math will do, is it'll give you basically a decent intuition about this modular arithmetic that'll help you solve these problems in your brain. So, how do I visualize this dumb stuff? 1, 0, 1, 2, 3, 4, 5, 6. Yeah, so this is your modular arithmetic circle. If I were to add 1 to 6, it would go to 0. If I were to subtract 1 from 0, it would go to 6. If I were to subtract 6 from 1, so starting at 1, and now let's go down 6 places. 0, 6. Well, I'm counting wrong. I should go 1, 2, 3, 4, 5, 6. Exactly the answer that you're looking for. So we can use, in our modular partial sum, we can use our point-to-point query to find at constant time the sum of any subarray we wanted. Again, constant time, without having to build up from the start. Which is important, because if we're not examining every single subarray, we're skipping some, then we can't use the building up from the bottom technique in the first place. We're going to need something that looks like this. So it's going to be inevitable. And this is just ideas that came into my head. They're not the solution. They're pieces of the puzzle. At the time, I didn't know whether it was a piece of the puzzle, but it was a potential piece of the puzzle that just came to me as amusing as I was thinking about the problem. So the next question is, okay, how the heck do we avoid examining every single subarray? That's at the core of the problem. And here's where the inspiration comes in. This is where the men and the women are separated from the boys and the girls. And let me tell you, it's kind of cool. So if we pick any one of these elements, let's pick this one. So first of all, what is the maximum sum of a subarray that we could possibly hope to achieve? That is going to be 6. So this is a very bad example because it's already a freaking 6. So let's pick another example, shall we? Let's pick this one. Now, like I said, what is the best possible sum that you can achieve? Well, if it's mod 7, the best sum you can ever achieve is 6. So that's the ideal that we are striving for. A 6 if we can get it. Okay, so we know we have a 1 here. Let's add a couple numbers to this to make it interesting. So this is a 5. I'm going to put another 5. That's the wrong freaking color. I'm going to put another 5 here. And that is going to bring the total up to 6. And then I'm going to put a 1. And that'll bring it back to 0. So 6, 0. All right. So we got a 1 here. Now we know that if we do a subarray that starts after this value and that ends on a 0, that result is going to be our ideal of a 6. How do we know that? Well, it's just our basic subarray arithmetic, right? 0 minus 1 mod 7 will give us 6, which is our ideal result. So if we choose any element, we actually can predict what end value we're looking for, what end value in the partial sum, the partial modular sum. That's interesting, right? Because that means that if we know the value that we were looking for, we can search for that value. There's a problem. These values, they're not ordered. They're not in a tree, right? Or any other kind of data structure that is searchable. The only search we could do is a linear search, and that's not going to give us anything better than what we got already. So, what do? Of course, what do you always do? You sort your shit. You sort your shit. You get your shit sorted, buckaroo. So, we're going to sort now these elements here. Now, if we sort the elements of our partial array, we're going to get a 0. We're going to get a 1, 1, 1, 1, 3, 3. Yeah, 0, 1, 1, 3, 3, 6, 6. And then once we have this, we know we're looking for a 0. So we can do a binary search. Well, actually, the binary search would look like this, right? It would look like this, something like that, right? We could do a binary search and we could find the value that we're looking for. And once we know that value, once we found it, we can say, okay, this one, if we start from this one, which is after this one, which is a 1, we know we can find a 0, and that will give us a sum of 6, the maximum that we can possibly have. Now, what happens if there is no 0? Well, in C++, there isn't actually a binary search function. There is a upper bound and a lower bound. And what they'll do is they'll get you close, like if you're looking for a 6, they'll get you close to the 6, or if you're looking for a 0, I should say, they'll get you close to the 0. But if the 0 doesn't exist, they'll get you to the next best thing. So what we're going to do is we're going to search for every value. We're going to search for the ideal that we want to see. And if that ideal doesn't exist, we're going to scan and find the next best thing. And that will be the best that we can do starting from this point here. And we're going to do that for every start point. Find the best that we can do. And the best out of all of those is the answer, right? Cool. So that means that we've got to find the best that we can do for n things. So we're at an n algorithm. But for every one of those, we have to search, which is log n. Which means we should be looking at n log n. And there you go. This is the meat of the problem. And you can see how it comes from that partial sum querying idea. That is what enabled us to do the sorting and to do the searching and to come up with our n log n solution. Now, there are some things that are important here. Let's say, so I got a 1 here, so I'm looking for a 0. There's no 0 here, but let's say there's a 0, I don't know, down here somewhere. I'm not going to change the numbers to make them match. Just assume. So then the 0 is going to exist here. I'm going to say, okay, I've got a 1 here. If I start from here, I'm looking for a 0 to get my best. I find a 0. But the problem is that 0 comes from here, which is before this one. That's no good, because if we start from here, we have to end on an element that's after here. But this element comes before, so that's no bueno. So what we need to do is when we sort our partial sum, we have to annotate every one of these values here with its index in the array. So this is 0, 1, 2, 3, 4, 5. And, then, I don't know, down here, it's going to be, I don't know, man, 0, and there's a 6, 1, 2, 3, 4, 5, I don't know, like that. We have to annotate each one of these so that when we sort them, we can still remember what index they came from, so that when we're searching, if we find our ideal or whatever, but it's before our pivot point here, then we have to ignore it and keep moving on to the next one, to the next one, to the next one. Now here's an interesting thing to note. We're going to be using the lower bound algorithm from the standard library. So it's going to find us the first value that is greater than the value we're searching for. So if we were searching for a 3, it would point us to here. And then what we're going to do is we're going to go to the left. We're going to go down and down and down until we reach the beginning of our sorted partial modular sum array thing. And then we're going to wrap around to the beginning until we reach this point here. So we have to scan through the values, but we got to scan through them circularly. The start and end point isn't just, it's not going to be searching from one end to the other. It's going to be searching from the middle around to the other end and back to the starting point, like this circular scan. And these are values in decreasing preference of what we would like to have. The most preferable value will be to the very left of what is returned from lower bound. So basically, again, the algorithm is we have this array of the partial sums and the values and everything. For every element, we loop through this array for every one. So for example, for this one, we're going to examine its partial sum value. We're going to search for the value that maximizes when we subtract. So for a 3, we would be searching for a 2, because 2 minus 3 is 2, 1, 0, 6, which is what we want. So we'd search for a 2, we do our binary search, we'd come here. This is the value, when you do a lower bound, this is the value, the first value that is greater than what we're searching for. And then we're going to scan to the left of that. And we're not going to find a 2, but we're going to find the next best thing, which is a 1. And that is going to be the best option for starting from here. So starting from here, you'd want to go to here. And that would give you 5, which is correct, right? 3 plus 9 is 12, mod 7 is 5. That's the correct answer. And you do that for every one of the values in here. And they would say, okay, so this, if we do it for this one, this is the case where we start from here. And if we do it for this one, this is the case when we're starting from here. And this is the case when we're starting from here. Find the best subarray that we can possibly have for each of these start points. And then we maximize, we choose the best out of all of those. And again, that's n log n. Now there is one thing that we have to be careful of, and that is this loop, each one of these iterations tells us the best starting from here, here. But what's the best starting from here, taking the entire array? That's a special case that needs to be addressed, and I'll show you that when we type the code out. But yeah, the case of sum over the entire array, starting from the very beginning, not starting from here or here or here, that will have to be, addressed separately, because that is not selecting any one of these as the subtractor. There is no subtractor, it's subtract 0. You just use the value here directly. So it's basically the maximum of all these values in here, which when you sort the array is just the very back element of the array here. That's what will be the best case for summing over the entire array, starting from the very beginning. Now here's one last thing to think of before we get into the coding here. And that is, all right, so when we loop through here, we're checking all these start points. When we try this start point here, we are going to be, we got a 6 here. So we're going to be looking for a 0. And there is a 0 here. But imagine this. Imagine there were no 0. Imagine this was like a 4. So this is a 4. Or I don't know. There's a 4 in here and this doesn't exist. Just bear with me. We're going to be doing this search here. Most of the elements are behind here. So when we do our search and we come, I don't know where we would start. We're looking for a 0, so we'd start here. We'd examine, we'd see it's a 1. That's okay. The 1, this is before the starting point. So then we'd go here. No, this is before. This is before. This is before. So you can imagine when we're going to hit the end half of our values here for their start point. Most of the values are going to be before. They're not going to be candidates. So we're going to have to scan pretty long through our array here in order to get the job done. In fact, the operation is going to approach big O of n as the number of candidates are moved, because we're going to check this one. We're going to say, no, it's before. 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 It's going to take us a long way to find the first one that is still open, which will be, corresponding to this or whatever. Doesn't matter. So what I'm thinking is we could actually inject some extra information into this scanning algorithm, and we can say, okay, we know the best solution that we've come up to so far. So let's say our best so far is a 5. And as we scan, the first element that we hit here, it's going to be our best chance. So let's say it's already been taken, which means in positioning, it comes before the pivot element. So it's not a candidate, but our best chance, if it were to be a candidate, let's say it only gives us 4, which is already worse than our best that we've encountered, which means that nothing else that we can get in this whole array is ever going to be better than our current best. And so we can just exit early. We don't have to keep scanning and checking and saying, okay, this one is not a candidate, this one is not a candidate, this one's not a candidate. Once we reach an element that is worse than our best, even if it's not a candidate, that's enough to tell us we're never going to do better than our best by scanning this. We should abort the scanning early. So that's a little optimization that we can put in here. I don't know if it's going to be necessary, but I think it's going to be interesting. So we need a way of translating these values now. Each one of these values needs to be translated into the same summing space that is used to calculate the best. You'll see it. You'll see what I mean when I get to the code. Maybe. I don't know. As you can see, it's a complicated problem. This is labeled a hard problem for a reason. It's not super easy. There's a whole bunch of different pieces you got to fit together. All right, so back to the code. This nested loop is gonna have to go. Oh, there's a little bit of a chili dog burp there. It's funny because my name's Snert. It's not chili, it's Snert, so that's weird. But anyways, what was I saying? Oh yeah. So first things first, we've got to build up our partial sum, our modular partial sum array. Now, that thing is going to need its own data structure because we have to annotate it with the indices for every element where it came from in the original input array. So let's create a struct. I'll call it modded partial. Need that in there. And so we want unsigned long for the partial sum at that point, and then size t for the index where it came from. All right, that's fine. And then we're gonna create a vector of modded partial. Call that impart. And we're going to create, impart.reserve. So it's going to need the same number of elements that are in our input vector. So we'll reserve input.size. And then we've got to do a partial sum. And we got to modulate that. So we could use partial sum from the standard library, but I don't think it's worth it in this case because we also have to apply the modulus. So let's just do unsigned long sum is equal to 0. This will keep the running total of the sum. And then from size ti is equal to 0 as long as I is less than input dot size I plus plus. We're going to loop through all of the inputs. The sum is equal to sum plus input at I mod. That was what we were doing before, basically. We know that we don't need that inner modulus because it'll never overflow from adding the sum plus one of the input elements. And we modulate afterwards. Then impart dot push back. And this is a structure we can use, what do you call it? Aggregate initialization. Sum and I. And there you go. So we've built up our array of annotated partial modular sums. Now we need to sort them by their sum. So that's simple, right? Sort impart.begin impart.end. Did I say that was easy? Because it's not, right? Because sort doesn't know how to sort an impart. It needs whatchamacallit? Needs that operator magic. So const modded partial right hand side const. Okay, so we're going to sort first by sum, but if the sums are equal, we're also going to sort them by index. So if sum is equal to right hand side dot sum, then we want to sort by index. Return index less than right hand side dot index. Otherwise, return sum less than right hand side dot sum. Okay, there we go. We have our operator. We have enabled sorting for our custom data type here. Now, here's the part where we get basically the best sub-range sum that we can possibly get starting at the beginning of the array, right? I mentioned this when I did the diagramming. That's going to be the very back of the sorted partials, modded partials. So let's do auto best is equal to impart.back.sum. So that's where we started off with. This is the best case from starting at the very beginning. Now we loop through every element and we choose the best case for starting at that element. So we do for auto I is equal to impart.begin. As long as I is not equal to impart.end, I plus plus. Now this might be a little different than you saw me doing the diagram. In the diagram, I was showing that we're looping through these elements here in the unsorted array. But it's the same elements in here that are in here. So there's no need to loop through them in their order in this array. It doesn't matter the order. You just have to make sure that you investigate each one of them. So we're going to loop through them in the order in this sorted array. And what we're going to do is we're going to do best is equal to, we'll call it ring scan. And we're going to pass in the best. So ring scan is going to have to do a bunch of things, right? It is going to have to determine, first of all, what is the target partial sum that we're looking for. It's going to determine the target, and then it is going to scan through the sorted impart and find the thing that's closest to the target, the maximum that we can get. And then it's going to return the maximum between what is the subarray that we can get from that starting point and the best one that we have currently. So it's going to need the impart array, right? Because it's going to need, it's going to need the whole thing to loop through. And it's going to need to know which element we're using as our pivot, which element that we're using basically as our exclusive start point. So that is I, right? Because we've got to check for each one of those. And it's going to need to know the mod that we're working with, because that is going to be used for a bunch of calculations. The mod is needed to calculate the target partial sum, and probably for some other things. I don't know. But yeah, that seems. And then we're going to return best. Okay, so I think this is all we need from our maximum sum, but we got to implement the ring scan. So unsigned long ring scan. Const vector modded partial reference mpart. So there's the entire sorted vector. And we need an iterator. So let's do our using vector modded partial const iterator is, got it backwards. That's, I was using the type def order, which is bad. Mpit. So that's modded partial iterator. Mpit. So we're going to need a modded partial iterator, and that is going to be an iterator pointing to the pivot. The pivot is my terminology for, you know, the current element being selected as the start point that we're going to now investigate subsequences. It's not really the start point, it's the element before the start point, if that makes sense. It's the one where we're going to use its partial sum to do the subtraction, and that is what's going to be used to determine the target optimum partial that we're looking for. Whew, it's complicated. It's very complicated. So we'll call it pivot. And then unsigned long best. And then unsigned long mod. Okay. So what do we want to do here? Well, first we have to calculate the target sum. What sum are we going to be looking for to maximize given the sum in the pivot? So this isn't, it's not super complicated. I mean, let's stick with our modular arithmetic mod 7. All right. And let's say our pivot sum is 4. So what value minus 4 mod, that's not, doesn't look like mod, there we go. What value mod is minus 4 mod 7 would give us our maximum, which is 6? Well, we just got to look at our number line here. If it were 1, if it were 2, 1, 2, 3, 4. No, that's not it. It would have to be 3. 3 minus 4 mod 7 would give us 6. So for a 4, we're looking for a 3. And it's interesting. For a 3, we'd be looking for a 2. For a 2 here, that would subtract 2, 1, 2. We'd be looking for a 1. Do you see the pattern here? It's just the pivot sum. So we'll call this one p sum minus 1. But what if the pivot sum is 0? Because if the pivot sum is 0, you're not going to move at all. You're just going to stay at that number. In which case, if p sum is equal to 0, then you're looking for a 6. So it's p sum minus 1 is the value, is the target value, unless p sum is equal to 0, and then your target is going to be a 6. So we just got to turn that into code, and that's not too freaking difficult. Const auto target sum is equal to, so we're going to do pivot pointer to sum. We're going to check, is that equal to 0? If so, we're going to return mod minus 1, right? In our case, if mod was 7, we wanted to return 6. Otherwise, we're going to return pivot pointer to sum minus 1. So there you go. We calculate our target. Once we have our target, then we find our starting point in the mpart array. We find a starting point. We do that by, you know, doing binary search. So const auto I disk. What does disk mean? Well, I mean the scan that we're doing, I've shown you before already. The scan that we're doing is kind of like cyclic. So if we have, you know, a bunch of values here and we're told the starting point is here, then we do this one, this one, this one. Then we wrap around to here, we do this one, and then this one is at the very end. So it's cyclic. This point here marks the discontinuity from the start here to the end here. So that's why I call this disc. Stands for discontinuity. But you could also think of it as a disc, you know, cyclic, circles, discs, whatever. Doesn't freaking matter. It's just a freaking name, okay? Upper bound. So we need iterator over the entire range. Impart dot begin, impart dot end, and we need the actual value that we're looking for. That's the target sum. There you go. So now we have an iterator to the discontinuity. That's the starting point for our cyclic scan through all of these modded partial sums. Now, iterators don't work like that. If you try to iterate past the beginning, you're going to get bad things happening. So we have to break this up into two iterations. One that goes from here to the beginning, and then one that goes from here to the discontinuity, from the end to the discontinuity. So I'm going to break this up into two iterations, and we're going to put those iterations in their own function. So we're going to do, again, best is equal to range scan. We did a ring scan, now it's a range scan. And we're going to do the range that we're scanning over. So that would be nPart.begin is the start of the range, and disk, iDisk, is the end of the range. We need to give it the pivot, because it's going to need that pivot when it does the scanning. And we're going to give it the best and the mod. It's going to need the best so that I can do that early exit optimization that I showed you before. And mod, I think it needs the mod. Yeah, it's going to need the mod to bring values into the same space as our best value here. Does that make sense? All right. So that's a range scan from the discontinuity to the beginning. And then we need another range scan. And this one is going to go from the discontinuity to impart.end. And again, it's going to need the pivot and the best and the mod. It also needs the best because it's going to, if the value that it finds in the scan is worse than the best, it's going to return that best into here. So that's what's used to build up. This is basically like a built-in std max. And then we just return best. Okay, so now we have to implement our good old boy range scan. So again, it's going to do unsigned long range scan. So we need an iterator to the start of the range, iterator to the end of the range, iterator, that's the pivot, and unsigned long best, and unsigned long mod. I'm usually not a fan of type defs or, you know, heaven forbid, #define for redefining types, but it's freaking annoying typing unsigned long every time. Just want to say that. All right, so now here's the thing. We've got iterators that point to our two ranges, but those iterators are start and end, and then start and end going in this direction. But we actually want iterators going in the opposite direction. So we have to use a reverse iterator. So what I'm going to do here is I'm going to do const auto reverse start is equal to make reverse iterator end. So the end is now going to become the start of our new reverse iteration. And const auto rend is going to be make reverse iterator start. There we go. So we're just going to get those out of the way there. And now we're going to loop from our start to our end. Now, the first thing that we want to do for every iteration, what we're doing here, by the way, is we're scanning across each of these values, and we're going to check to see if it is a candidate and if it will be, you know, the value that will give us the best subrange for a given starting, for our pivot, basically. For a given pivot, what is the best subrange modded sum value? Now, we also want to do our early exit. So we want to compare to our historic best, and if we ever encounter a value that's worse than our historic best, we're never going to do any better than that because they only get worse as you scan. So we should exit early with the historic best. But the problem is, these partial sums here, the values that we're iterating over, they are the sums taken from the beginning of the input array up until, you know, some point. But what we want is the sum taken from the value after the pivot to that point in the original array. So we have to subtract the pivot sum from the sum here to get the actual sum over that subrange, and then we can compare that to best. Now the problem here is if we just do a subtraction, it's not going to work good, right? Like let's say the value that we have is a 3, we subtract 4, that's -1. -1 mod 7 is, I think that's still -1 in C++. Modular arithmetic is weird for, you know, signed values, negative values. And the other problem with this is that we're working with unsigned values to begin with. So even if we didn't have that problem, it wouldn't go to -1. It would overflow to some truly enormous number. And it wouldn't be good for our purposes. So the question then is, well, how the heck do we do this subtraction? The answer is, what you actually do, well, let's look at it. 3 minus 4 mod 7 should give us 6, right? So what we do is we take 3, we add 7. So we add 1 mod interval. Now, adding a mod interval to a value, in modded arithmetic, 3 and 3 plus 7, which are 10, are actually the same value. So we haven't changed the value in terms of modular arithmetic. But what we have done is we've added some padding. So now when we subtract 4, we get 6, which is the actual value that we're looking for. Now there's a problem here, and that is the value that we subtract, it's possible, usually it's going to be more than this value here. But it's also possible that it'll be less than the value. For example, 3 minus 2 mod 7. So if we add 7, 3 plus 7 minus 2, that would give us 8, which is bad. So we have to mod 7 again. We have to mod 7 after we do this addition subtraction, and that'll give us 1, which is actually the same as just 3 minus 2. So we add the padding to prevent underflow, but then afterwards we have to mod for the case where this value, the subtraction value, was less than the subtractand. The subtractor? What are they called again? I don't know. It doesn't matter. You get what I'm trying to say. So we have to calculate what is the actual sum based on the pivot. So that is going to be const auto sum is equal to I, pointer to sum, plus the mod for the padding, minus pivot pointer to sum. And then we mod again to make sure that, you know, we haven't exceeded the modular space. And there you go. This is the sum that we would get with this element. Now we want to compare that with our best sum that we've seen so far. So if best is greater than or equal to sum, then there's no hope to be found here. There's no gold in these mines. So we're just going to return best. Now, if not, that means that there's still hope. So the next thing that we have to do is we have to check to see if the element that we are examining is after the pivot in the original order. So we do else if I, pointer to index, is greater than pivot, pointer to index. And if it is, that means that it's a candidate. It's also better than our current best, so we should return some, because it's the best one. As we scan, the options only get worse and worse. So once we find a viable option that's better than our current historic best, we return that immediately. And then we're done. And here, we're just going to return best. This is the option if you scan through the entire array and you didn't find any, and you didn't find any that were worse than the best, but you also didn't find any that were actual candidates. I don't think it's possible to reach this point, but it might be. And just in case, we just return the current best. We never found anything anyways, so just return what we had, basically. And there you have it. I think that's everything, right? We haven't defined any new functions in here. So that should be it. Now, let me see here. All right. Well, I guess that's it. Let's try and build it and see what shakes loose. I mean, I've written a lot of code. I'm not, compilation error. No one is less surprised than I am for that. All right, make reverse iterator was not declared in this scope. All right, it turns out that apparently make reverse iterator is a thing from C++ 11. But we're not in C++, no, C++ 14, but this one is, I believe, C++ 11. So we're going to copy all this. We're going to go down to C++ 14, which I believe, I knew, I've been caught by that before. It removes all your code. Then I'm going to paste this in here, and it should work, I hope. Compilation error, okay. Well, at least it didn't tell us anything about make reverse iterator. So I think we solved that one. Now, what is this total utter horse poopy? God damn, I hate template errors. Normal iterator, mismatch types. Template argument deduction failed. Algorithm. Operator less than. Okay, so buried in this terrible wall of text, we have upper bound, and it's telling us it can't find, and comparator is having problems comparing things. I think I know what the problem is, but I just want to take this moment to get on my soapbox and say that once the standard library has been re-implemented with concepts, this is not going to be as much of a pain in the penis as it usually is. Concepts for the win eventually, but for right now, we've got to grin through the pain. So the problem is we're doing a partial. Yeah, we're doing upper bound here, upper bound, and that needs to compare an unsigned long with an M part, but those are two different things. It doesn't know how to compare them. It knows how to compare a modded partial with another modded partial, but doesn't know how to compare a unsigned int with a modded partial. And I believe the unsigned int has to come first, so we can't make it a member, much to my chagrin. We're going to make it a free function, bool operator less than unsigned long left hand side, const modded partial and right hand side. And we're just going to return left hand side less than right hand side dot sum. Okay, that should maybe solve the problem. Let's try it. All right, it solved the problem. We have compiled, and we've also handled all of the sample test cases. That doesn't mean that we're going to work on all the big ones. There might be corner issues that will crop up when we run on a huge data set, but it is quite promising. It's a glimmer of hope in the distance. So let's just let these tests run. We'll see all the greens rolling in. And you know what? Congratulations, you have earned 65 points. Couldn't you have freaking made it 4 more? Just saying. So there you have it. My recording thing, I don't know if you can see this if I move it into the window, but it's looking at about 1 hour, 40 minutes. And there wasn't a lot of dead air in this recording. I didn't take any big breaks or anything. My throat is telling me I didn't take any big breaks. So that means that this is probably going to be a long video. And now maybe you can get a reason for why I don't just, do the hard problems. Because if you want to explain them fairly well, it takes a long time. And it also, because this is me explaining it after I had already solved it. So if I had to try to solve this live, while recording, while having to talk, while also thinking of fairly complex issues, it's just not going to work. So this is why I don't generally solve. This is why I stick to the interview preparation kit. Those ones are much more realistic. They're problems designed for people to be able to solve on the fly in a stress pressure situation like an interview. They're more realistic to what you would actually see in an interview situation, so they're more useful for most people. But these problems are fun. I will not deny that they're fun, and I would spend more time of my life solving them if I didn't have other things to do that generally were more, that yielded me more profit. But that being said, I still recommend you try some of these if you're interested. It's a fun puzzle. I mean, if you're wasting your time, I'm not going to say wasting your time, but you know what I mean. Spending time idling the hours away playing, I don't know, Sudoku or playing Overwatch or something, and you like programming, you might have a better time, challenging these problems because they really challenge your problem-solving skills and your ability to identify and pull together disparate techniques, synthesize them into a cohesive solution to a problem, fairly complicated problem. I mean, I like these kind of problems. The statement, not super complicated, not super convoluted, but it requires a little bit of ingenuity in order to pull it off. And I hope you like this one because it's gonna be maybe the last one of its kind. I don't know, I might do more hard problems, but for the most part, sticking to medium and maybe some easy. And also, I'm not gonna, like I said at the beginning of the video, I'm not going to be taking any suggestions, any people want me to solve their freaking homework for them. Nah, that's not happening. This was a one-time thing. I played myself. I knew I shouldn't have even read the problem statement, but I couldn't help myself. I clicked that link, and once that problem got in my head, I couldn't give up until I had solved it. And once I solved it, I just couldn't help but making the video to share it. So here it is, the first and last of its kind. Hope you enjoyed the video. If you did, please click the like button, it helps a lot. And I will see you soon with some more coding challenges.